Atoms are the fundamental building block of matter. So now we're going to talk a little bit more about the atom, specifically the subatomic particles that are present in every type of atom that exists. So elements are composed of a specific type of atom. For example, element carbon is composed entirely of atoms of carbon. And the same thing for hydrogen. The element hydrogen is composed entirely of atoms of hydrogen. What the atom for different elements they have in common is the type of subatomic particles that they have present. For example, an atom of carbon is going to have the same three types of subatomic particles as an atom of nitrogen. Those subatomic particles are the protons, the neutrons, and the electrons. What is different between the atoms for different elements is the amount of each subatomic particle that they contain. So in the table here, I'm showing you the three different types of subatomic particles and some of their properties. The mass for the protons and the neutrons is a number that is equal to each other, 1.67 times 10 to the minus 27. Those masses on the table are given in kilograms. And then you have the mass of the electron as 9.1 times 10 to the minus 31st. There's a value for the charges, and you get to see that for the protons and the electrons, we have a very similar value for the charge of those particles. And for the neutrons, we have a numerical value of 0. The difference between the charge of a proton and an electron is not the magnitude of the charge, but the sign of the charge. For protons, we have a positive charge. For electrons, there's a numerical value that is a negative number. Now, if, for example, an atom of carbon, right, it has these three different types of subatomic particles, right, and that's all it contains, we can think about the mass of the atom of carbon as the addition of all of the masses for the subatomic particles that are present in that atom of carbon. So what I have here is just an equation adding all of the masses, right? Starting here. Whenever you look at the periodic table where you have organized all of the elements, right, starting with hydrogen, element number 1, you have information, right, for all of them. We have the atomic number usually on top of the symbol. Under the symbol, we usually have the name of the element and also the mass. For this representation that I have here, that number is the mass, but usually that mass is down here. Now, we can actually find out the total number of protons, electrons, and neutrons, all of those subatomic particles for an atom using the periodic table. The symbol that we use to represent protons is the letter P with a positive sign. So the atomic number that you get to see on the periodic table for the different elements is actually telling you the number of protons for that element, or the number of protons that every atom of that element contains. For example, for carbon, atomic number is 6. It means that carbon contains 6 protons, an atom of carbon. So I have 6 times the mass of the proton, because an atom of carbon contains 6 protons. So if I want to get the mass, right, and the atom only contains those subatomic particles, I can add those masses and I can have the mass of that atom. The mass that we get to see on the periodic table for the elements is actually telling you the total number of protons plus the neutrons. So what I'm trying to go over here in this calculation is how those numbers, right, are being obtained. So for example, for carbon, we have a number that is very close to 12. So I'm just rounding that number to 12. That's the mass number. The atomic number that you get to see in the periodic table is telling you the number of protons. So atomic number is 6. And then we can actually use those two numerical values to find out the number of neutrons. If the mass is protons plus neutrons, then the mass minus the protons is going to tell you how many neutrons you have for that specific atom. So looking at carbon, the mass is 6, the number of protons is 6. So to find out the number of neutrons, we have to do 12 minus 6, which is the atomic number, which is telling you the number of protons, and that's going to tell you that the atom of carbon that we're looking at, it contains 6 neutrons. So that 6 right here highlighted in green is representing the 6 neutrons that you have in the atom of carbon. So the 6 neutrons, each one has a mass equal to 1.67 times 10 to the minus 27 kilograms. So when I do my multiplication and then I add everything together, I'm getting this number here. That number is representing the mass in kilogram for the 6 protons plus the 6 neutrons for carbon. And we know that we have the 3 different types of subatomic particles, not just protons and neutrons. I'm adding just the protons and the neutrons for a reason. Maybe it is not too obvious that the masses for the protons and the neutrons, right, are a lot bigger than the mass that we have listed there for the electrons. If we focus only on the numerical part of the scientific notation, right, the mass for the electron is 9.1, which is bigger than the 1.67. But the exponential part for the electron is minus 31st. So the mass of the protons and the neutrons is actually a lot bigger than the mass that we have for the electron. The difference is so significant that, look, when I calculate the mass for the atom of carbon just considering the protons and the neutrons, I get 2 times 10 to the minus 26. Now, if I add the masses of all of the electrons that we have in an atom of carbon, which is 6, right? And we're going to learn why it's 6 electrons for carbon. If I add all of those masses, look, adding this part here, that corresponds to the masses of all 6 electrons in an atom of carbon, I'm going to get exactly the same number. I have the same mass calculated using only protons and neutrons than the number that I'm getting if I add also the electrons. I'm getting the same numerical value for the mass because the mass of the electrons is so small that it's actually not making a difference on that total mass that I'm calculating. Now, that mass that we get to see on the periodic table, that 12, right, is not the mass in units of kilograms. And we can see this with the example. When I'm calculating my mass here, that's the mass. When I'm adding the protons and the neutrons, I'm getting a number times 10 to the minus 26. That's not the number that I have here on the periodic table, not at all. Okay? The number that I have on the periodic table is not a number in units of kilograms. What I'm calculating here, that number that is super small, without the electrons here or with the electrons here, right? Times 10 to the minus 26, it's a super small number. That number has units of kilograms. The number that we get to see on the periodic table, it's a different unit. Okay? We actually have two different units that we use with that number. Depending at which point we are during the term, we're going to see different units for the number. Right now, we're going to be using that mass as atomic mass units. That's going to be the unit that we are going to assign to the masses that we have for the different elements on the periodic table. Or AMU. So if the mass of the different elements is given in atomic mass units, right? Just the definition for atomic mass units is the mass of one single atom of carbon, right? We calculate that mass in kilograms, which is the addition of the masses of the 6 protons plus the masses of the 6 electrons for the atom of carbon added together. If we divide that number, which I calculated here in kilograms, if that number is divided by 12, I'm going to get a numerical value equal to 1.67 times 10 to the minus 27. In the previous table, where I have the masses in kilograms, that number right there actually corresponds to the mass of one proton and also to the mass of one neutron. So by definition, one atomic mass unit is the same as 1.67 times 10 to the minus 27, okay, which is the mass that corresponds to the protons and the neutrons. So instead of using those masses in kilograms, which are numbers super small, we're going to use masses as one. For example, the mass of a proton is defined as 1 AMU. Mass of one neutron is defined as 1 AMU. We already saw that the mass of the electron is so small in comparison to the protons and the neutrons that it doesn't affect the mass for the atom. So using atomic mass units, we're going to define the mass for the electron as 0. Now, in the previous table, we also saw that the charge for the protons and the electrons, it has a very similar numerical value, but with opposite signs. So instead of using those charges, we're going to define the charge of a proton as positive 1, the charge for the electrons as negative 1, and then the neutrons, they don't actually have a charge, they're neutral. Okay? So we assign a charge equal to 0 to the neutrons. This information here is extremely useful because now when we look at the periodic table, instead of thinking about that mass for carbon as 12.01 with an actual unit of mass, we're going to look at that number in atomic mass units. So we can actually use that number to find out the number of neutrons that are present in any atom if we're looking at the periodic table. So that's the atomic number, which is telling you that you have 6 protons. That right there is the mass in atomic mass units. The mass is protons plus neutrons. Therefore, the number of neutrons is the mass minus the protons, which is given by the atomic number. Okay? Just to review some of the things that I mentioned in the previous slide. Some other important information about what we get to see on the periodic table for each element. We have the atomic number, which is telling you the number of protons, but we also know that atoms are neutral. It means that they don't have an overall charge. We have 3 types of subatomic particles in general. Out of the subatomic particles that we have present in all of the atoms, right? We have particles with positive charges, which are the protons. We have particles with negative charges, which are the electrons, right? The neutrons, they don't have an overall charge. So for an atom to be neutral or to carry an overall charge that is equal to 0, it means that all of the positive and negative charges, they're canceling each other out. Okay? So if we can determine the number of protons looking at the periodic table, because that number is given by the atomic number, then we can also find out the number of electrons, because we know that atoms are neutral. So if, for example, carbon contains 6 protons, that's 6 positive charges, because each proton has a charge equal to +1. So for an atom of carbon to be neutral, if it contains 6 positive charges, it has to contain 6 negative charges. So the electrons are those negative charges. So for atoms to be neutral, what that means is that the number of protons and electrons are equal to each other. So the atomic number, which is equal to the number of protons in neutral atoms, is going to be equal to the number of electrons. So when I was calculating the mass, right, for an atom of carbon, I added the masses for the protons, 6 protons, plus the masses of the 6 neutrons, and then I added the masses for 6 electrons. At the moment, we didn't know why I'm using 6 electrons. I mentioned that atomic number is telling you the number of protons. I mentioned that the mass minus the number of protons is telling you how many neutrons, but we didn't know why I was using 6 electrons. Now, the reason that I was using 6 electrons is because the atom of carbon is neutral, so since it contains 6 protons, it has to contain 6 electrons. The number of protons, which is the atomic number, is actually giving you the identity of an element. When we look at the periodic table, each element has a different atomic number. Hydrogen is 1, and then we have carbon 6, nitrogen 7, helium number 2. So each element has a specific atomic number, which is telling you the number of protons. So we don't have atoms of different elements with the same number of protons, right? We have all atoms of hydrogen with 1 proton. That's the atomic number for hydrogen. All atoms of nitrogen with 7 protons, because that's the atomic number for nitrogen. Now, out of the 3 subatomic particles, we can have atoms of the same element with different number of neutrons or with different number of electrons. But atoms of the same element will always have the same number of protons.